my slides. So maybe want to start today with just some, announcements and then some discussion of what we're going to do for the next few weeks. So give me a second to pull up some things here. Right. So as usual, we'll have the lecture notes are posted online already. We have virtual office hours that'll be taking place after class today and then also at 4 p.m. The mentor sessions are at the usual time, usual place. So Sunday, Monday, Tuesday, and Thursday. The next homework assignment is due today by 5 p.m. If you can't make it for one reason or another, if you feel that you're too busy to work on it, I would say don't stress out. I know that everybody's really, really stressed out and busy doing other things. I know I'm definitely very behind. So if you can't turn it in today, no big deal. Just turn it in whenever you can. The last problem set will be due next week, next Wednesday. But the homework assignment due today is the last problem set. So definitely no more assignments, no more homework assignments after this. And here, give me 1 second. I realized that the slides I'm showing are actually not the slides I want. So 1 second just to change things here. Right. Okay. Let's do something to fit. Okay. So just as a reminder, I did send this out over Sakai that you have the option of taking either the second midterm or giving final presentations. If you do want to just do the midterm, then I will post it next Friday. So that'll be a week from today, and then it'll be due the Monday following that. So you will have the weekend to work on it. If you need more time for any reason, I am totally flexible. So I would say don't stress out, like if you need a couple more days because anything crazy is happening. For those who are going to give the final presentation, as I've mentioned before, please do the following 3 things. Number 1, choose a group of 2 to 4 people. Number 2, pick a topic. And number 3, think about creating a 20-minute video. So you can either have this video to be recorded or you can just go ahead and do things there in class. I think it looked like maybe 5 people or so wanted to do some video presentation. Please let me know as soon as possible. And really, I would like to know by Monday if you do want to do a video. That way we'll have an idea of what's going to happen in class, and then I can kind of plan for the rest of the semester. But please let me know as soon as you can if you do have an interest in giving one of these video presentations. For the midterm, there was a question sent to me, is it going to be open book, open note? It'll be just like the first midterm. So you can take as much time as you want. There are only going to be 3 problems that you'll have to do, but just like with the first midterm, I am considering this to be like the take-home portion. So you can use whatever notes you want to work things out. Right. Okay. And please remember here for the presentation and for the midterm that you will receive extra credit if you decide to do both. So I would say don't stress out that if you want to do both, that'll certainly be great. What I want to do is talk about the calendar and how things are going to work for the rest of the semester, because some of this will be dependent upon how many people will decide to do a final presentation. So remember that homework set number 12 is due today. This is the last homework assignment that you'll have to turn in. Today I will lecture. I'm going to finish up some ideas about properties of continuous functions. But on Monday, this will be kind of a free lecture. I'll talk about countability and the real numbers. So this will not be covered on the midterm. You don't have to worry about it. I just figured that since that will be my last official lecture, I wanted to give kind of a fun lecture that talks about what is the idea of saying that a set is countable? Why is it that the real numbers are uncountable? And then there's some applications here actually to computer science that may not be totally clear, at least not obvious at the very beginning. So for those who are CS majors, I'm hoping that you'll actually enjoy the lecture on Monday. But as far as I'm concerned, what we've been covering the last few days, because it hasn't really been on the homework, it won't be on the midterm. So I will give a midterm review on Friday, and I'll have a packet that I'll pass out in a few days with more information. But again, Monday, I just consider that to be kind of a free lecture. It's just supposed to be for fun. So I would say don't stress out about things. However, on Wednesday, I do want us to go over problem set 6. So the plan on Wednesday is to actually do solutions to the problems. And I want us to try our best to make it through as many problems as we can for problem set 6. So please try your best to work on the problems, come up with solutions, so then we can present them in class on Wednesday. Right? So Friday at the end of next week is when we'll do the midterm review. So I'll try my best to cover, at least touch on the topics that we'll need to know. And then in about a week and a half, starting Monday the 27th, there will be no more lectures. That's when we'll have the final presentations. So for example, if there's only one person who's going to give, or one group that'll give a final presentation, we'll have that presentation for 25 minutes, and then the class is done. If there's 2 groups that present, they'll both present on Monday, then the class is done. But really, as far as I'm concerned, once we finish with the final presentations, then that's it. The class will officially not meet anymore. So that's part of the reason why I want to know who was going to give a final presentation, so then we'll have a better idea of how many times we're going to meet in another week and a half or so. Okay, so any questions on the calendar here? All right. Okay, so let's maybe go ahead and get started on some of the material. So I want to do a quick recap of some of the ideas that we talked about on Wednesday, some of the concepts that we had. The reality is there actually were 3 main theorems that we worked through. And today I want to focus on those theorems in a bit more detail. So first, we talked about the intermediate value theorem. So this says, say that we have a continuous function, let's call this here f, and let's pick a number, L, that's between f of a and f of b. Then the statement is that there exists a point in the interval such that f of p equals L. Right, so in other words, f attains all of its intermediate values between f of a and f of b. So that's the statement of the intermediate value theorem. Second statement we made is the boundedness theorem. So this here says, say that we have a continuous function f, then it says that our function is bounded. So that is that there exists a lowercase m and an uppercase m that acts as a lower bound and an upper bound respectively. Right, so again, the boundedness theorem says as long as you work on a closed interval, then your function is bounded. And our third theorem was the extreme value theorem. So this says, given a continuous function, again on a closed interval, then not only is there an upper bound, but there exists an element c in the interval where I can hit that upper bound right on the nose. Similarly, there is not only a lower bound, but there's an element d in the interval where I can hit that lower bound right on the nose. Right, so that is that f attains its extreme values, its maximum value and its minimum value. All right, so I want to emphasize that all 3 of these here work as long as you're working on a closed interval. If it's not a closed interval, then these statements here are not true. Right, so you do want to be careful to work on a closed interval. Okay, what I want to try to do is maybe just draw a picture. So this is the exact same picture that I gave last time that really is going to hit home. What do I mean by extreme values? What do I mean by boundedness theorem? Right. So here, what we're going to do is let's take a look at an interval, maybe here from A to B. So perhaps this here will be my element B, and let's say maybe this over here will be my element A. Right, so here I have my interval from A to B. So here at A, of course, this is going to take on some value. And this here is what we're calling f of A. Sorry, this is not the easiest thing to do. Okay. Okay, so again, that's my value f of a. And then similarly here for b, I'll come down here, and then here I'll have some value here, f of b. All right. So first, my intermediate value theorem says that if I were to pick a value L between f of a and f of b, any value at all, then that has to correspond to some point here, P. Right, so there's some point P that matches up to this L. Right? The boundedness theorem says that there is an upper bound and a lower bound. Right, so maybe let's call this here capital M. And we'll call this here lowercase m. Right, so I want to make sure that here in this interval that it never gets any lower than m and it never gets any greater than capital M. Right, that's what the bounds here mean. Put this down here for lowercase m. Okay, so again, there's going to be two bounds, lowercase m and uppercase m, where all of my values lie in that range there. And the final statement says that if I actually do take a look at, say, the lower bound here, then this here has to correspond to some element d. Right, so this lower bound here is my f of d. And then I have my upper bound here, and that has to correspond to some element c. Get rid of this. Right, so again, this here has to correspond to f of c. Okay. All right, any questions on these three statements here, intermediate, boundedness, and extreme value? All right. Okay, what I want to do next is actually give some applications of all of this. So there's a couple of theorems that I want to prove here that will build upon these three theorems. So the first here simply says, on a closed interval, the sum of two continuous functions is a continuous function. Right? So I want to present the proof here in exactly the same way that we did this for Cauchy sequences. So hopefully you'll see that there's kind of a general trend of how all of this goes. So remember that if I want to prove something is continuous, I really need to work in three statements, because this is part of my epsilon delta proof. So let's say that epsilon here is given, right? Some positive epsilon is given, and just pick an element in the interval, call it P. Now, I need to explain how to choose delta. So the way that we'll do this is, well, of course, I'm going to bound for f minus fp is less than epsilon over 2 whenever x minus p is less than delta 1. And then let's bound g of x minus g of p is less than epsilon over 2 whenever x minus p is less than delta 2. So again, hopefully this looks very similar to the way that we did this for Cauchy sequences. I have my delta 1, have my delta 2. That kind of tells me what my delta should be. So now we just work out the proof. So we state whenever x minus p is less than delta, then we'll take a look here at the sum of the functions, right? F of x plus g of x minus f of p plus g of p. So we can use here the triangle inequality. Right, now we have this sum. So again, using the triangle inequality. And of course, this here is all going to be less than epsilon. But that's exactly what we wanted. right? If x minus p is less than delta, then we have the sum here, f plus g of x minus f plus g at p is less than epsilon. Okay. So again, the proof here is very, very similar to the way that we work this out for like Cauchy sequences. Right. So any questions here on this first statement, that the sum of two continuous functions is continuous? Okay, all right, let's keep moving then. Now let's take a look at the product of two continuous functions. So it's almost exactly the same statement. Right, if I have two continuous functions, f and g, on a closed interval, I want to emphasize now I really am going to use the assumption that it's on a closed interval, then the product here is a continuous function. Okay, so the proof is very similar. So we start off by saying, let's assume epsilon positive is given. Let's pick a point P here in our interval. Now we're going to do a little bit of work to figure out what should our delta be. So first of all, the boundedness theorem says that I can find m1 and m2 so that my f of x is bounded by m1 and my g of x is bounded by m2 for everything in the closed interval. Right, so again, here I'm using the boundedness theorem to know that my functions f and g are bounded. So I can find these bounds, m1 and m2, where this works for everything in the interval. Okay. Now, here's how we're going to choose our delta. Right, so as you probably are going to guess, delta here is going to be the max of 2. So first, let's maybe choose delta 1 so that we have this bound here, f of x minus f of p is less than epsilon over twice m2. Right, so like last time we had epsilon over 2, but now we're going to work with twice m2. So I'm going to introduce something a little bit different here. Similarly, I can find a delta 2 where for g, we have g of x minus g of p is less than epsilon over twice m1. Okay, so again, g of x minus g of p is less than epsilon over twice m1. And that's where the delta 2 is coming in. So if we have these, now we just work out the proof. So if we assume that x minus p is less than delta, then we want to take a look here at this difference, right? F times g at x minus f times g at p. And now we just do a clever trick and use the triangle inequality. So that will be less than or equal to this here. Right, so f of x minus f of p times g of x, f of p times g of x minus g of p. It's just a clever trick to kind of get everything to work. And so of course, for the first one, for fx minus f of p, this is where I get this epsilon over twice m2. For g of x, this is where the m2 comes in. For f of p, this is where the m1 comes in, and the g of x minus g of p, this is the epsilon over twice m1. And then of course, everything just combines together, and then this here is just epsilon. Okay, any questions on how we work this one out here? And hopefully this looks familiar. This is exactly the same way that we did this for Cauchy sequences. Exact same trick. Okay, so remember when we did this with Cauchy sequences, we realized that we have things like addition, we have multiplication, so we could form a field. So we're going to try to do something similar here now. So now this says, again, let's focus on a closed interval I, and let's take a look at the collection of all continuous functions. So I'm using this notation here, C0 I comma F. So this means the set of continuous functions that go from I to F. Right? They start with an interval I, they end in a complete ordered field, namely F. So then the statement is that the collection of all continuous functions forms a commutative ring. So what I want to do is kind of remind you what's really happening here. Now, remember, we want this to look very similar to like the Cauchy sequences. So it should be clear that we've already proven a lot of stuff, like things like closure. So we know that if we have two continuous functions, the sum is continuous. If we have the product of continuous functions, two continuous functions, then their product is continuous. We also know that like commutativity holds, so it doesn't matter with addition. Commutativity holds for multiplication. We have associativity for addition. We have associativity for multiplication. We can even say that we have a zero element, namely it's that function that sends everything to zero. Right, so it's the function where f of x equals 0 for all x. Similarly, we even have an identity element, because it's that function that sends everything to the number 1. Right, so f of x equals 1 for all x. So that means we've actually proven all of this. There's only one that we really haven't proven, and that's this one here about inverses. So it turns out that this F9 we have to cross off, because this is not true for continuous functions. If you have a continuous function, it is not true that 1 over that is a continuous function. Right? If you don't believe me, take a look at the function f of x equals x and think what happens to 1 over x. Right? 1 over x is not continuous when x equals 0. So that's a problem. So it just turns out that if all 10 of these were true, then I would call that a field. But if I assume that only one of these, I said 13 axioms, it should be 10 axioms. If one of these is missing, namely if multiplicative inverse is not true, that's just what we call a commutative ring. Right? A commutative ring with inverses is just what we call a field. Okay. Right. So you may see this in other classes at some point, especially those here who are interested in going on to to the abstract algebra course. This is one of the examples that typically comes up in a class like that. Like the whole set of continuous functions forms a ring, but it's not necessarily forming a field. So I just wanted to kind of say that we've actually done a lot of work. It's just that this F9 here is not true. Okay. All right, so any questions here on this statement, how we can put everything together here to do some arithmetic? Right. Now, we don't have to take a look at all continuous functions. The set of polynomials is actually pretty interesting in itself. So I claim that every polynomial is a continuous function. Now, I actually wanted to prove this using induction. So this will be a way that we're going to kind of combine a couple of different techniques. We're actually going to combine induction, and we're going to combine epsilon delta. So I thought that it might be kind of nice, as we wrap up the class, to actually see how both of these could be used together in one proof. So what we're going to do here is prove the following statement by induction. If f of x is a polynomial of degree at most n, then f is continuous at any point. Right, so again, here I'm going to say if it has degree at most n. So for example, the coefficients here could all be 0. I don't really care. The leading coefficient here, an, that could be 0. So I'm just going to say at most n. I'm not going to worry about saying the degree is exactly n. Okay. All right, so remember that to do a proof by induction, we need to do base case, state the inductive hypothesis, and do the inductive step. So let's start with the base case. So I want to take a look at polynomials with degree at most n minus 1. All right, so in some sense, I'm going to start with n is equal to 1. So these here are linear functions. So we're going to prove that this here, f of x is ax plus a0, is continuous at p. Right, so we're going to start by proving that every linear function actually is continuous at p. Okay. So remember that if we want to prove something is continuous, we have to do 3 steps. Say, let epsilon be given, write down your delta, and then prove that everything works. Right, so let's do that. Let's say epsilon is given. Let me choose delta in this way. So delta here is epsilon divided by absolute value a1 plus 1. And I'll say in just a moment why I'm choosing this absolute value a1 plus 1. Okay. So if we choose this as our delta, then if we assume that x minus p is less than delta, then we find f of x minus f of p. So just plug in what f of x is here. Turns out that the a0s are going to cancel. And so we can write this here now in terms of a1. But now let me substitute back in that x minus p is less than delta. I'm going to substitute back in what delta was. And so then we find this. Now, here's the subtlety. It's just kind of a slick idea of a proof that you may want to keep in mind later. You might ask, why do I have this plus 1 in here? Well, if I don't have the plus 1, then I would just find a1 divided by a1 times epsilon, and then that's just equal to epsilon. So I could just have left it at that, right? That's just equal to epsilon, I'm done. However, what if a1 is equal to 0? Well, if a1 is equal to 0, then I can't just say let delta be epsilon divided by a1, because I can't divide by 0. However, if a1 is 0, then f of x here is just a constant, and then this over here is just equal to 0. And 0 is always less than epsilon. So what you might be thinking is, well, why not just break it up into 2 cases? What if a1 is equal to 0? What if a1 is not equal to 0? Well, you'll see here, this trick works for both cases. Because if a1 is equal to 0, then delta is just equal to epsilon. And then here, it actually doesn't even matter what delta is, because then here I would get the 0, right? This here is still 0. This here is still 0, and that's less than epsilon. So it's just simply saying that if I do this clever trick here of writing a1 plus 1 in the denominator, then I actually take care of the case when a1 is equal to 0. Right, so you could easily have done 2 cases if you wanted to, but just saying that here we've actually decided to write it. So I've actually taken care of both cases at once. Okay, so proposition Pn here is true when n is equal to 1. Right, so any questions on how we prove here that linear functions are continuous? Okay, all right, so let's try to move on now. So we just proved the base case. So now let's just state our inductive hypothesis. Right, so we're just going to state that Pn here is true for some n equals m. Okay, right. So now we're going to do our inductive step. So let's say n is equal to m plus 1, so this is the next case. then any polynomial of degree at most n can be written in the following way. So this is a polynomial of degree at most n, but now I'm going to do a trick. If I subtract off the constant term, then I can write that as x times a polynomial of lower degree. So again, here I have an x times this polynomial here plus a constant polynomial. Okay. So now let's just make some observations. G of x has to be x, right? That's just going to be my definition. So that was this first term here. And C of x, A0, that's the last term here. Both of those are continuous because we just proved that every linear polynomial is continuous. So those are both continuous because of proposition P1. Right? Now moving on, let's take a look here at this h of x, which is what we wrote here. If you stare at this, this has degree m, at least degree at most m, and that's continuous because proposition Pm is true. Right? Now, the product, h times g, is continuous because we just proved that the product of continuous functions is continuous. So then let me take a look here at the sum. So I know that g times h is a continuous function. So I'm adding a continuous function with another continuous function, c of x. But we just proved that the sum of two continuous functions is continuous. So f of x has to be continuous. So then that means now the proposition Pn has to be true. Right? Okay, does that kind of make sense as a proof then? Okay. All right, so again, now we know every polynomial is a continuous function. So we can just totally take that for granted, that every polynomial is continuous. So let's take a step back. Now that we've kind of put all of this stuff together, like what does this mean? What is it that we've done so far? All right, so we've seen examples of functions which are continuous at every point. Right? Those examples are polynomials. So it doesn't matter which P you chose. Notice I didn't say anything about continuous on a closed interval. I said continuous everywhere. They're continuous at every single point. So like if you wanted an explicit example, you could take this here. So sorry, this should be a 3x squared. So x cubed minus 3x squared plus 2x. Right, there we have a polynomial that's continuous at every point. On the other hand, there are functions which are discontinuous for a lot of points. So for example, what if I take the ratio of two polynomials? So if you wanted to see an example, you could take this one here. F of x is x divided by x minus 1. That function is discontinuous when p equals 1. And so in fact, you can actually create more and more examples. I can find you a function that's discontinuous at a point p by just looking at things like when this denominator is equal to 0. Right, so I can find a function that's discontinuous at lots and lots and lots of points. Right, so I just want to show some graphs of these two examples to kind of hit home what's what. So this first example here, right, is of course what's over here on the left-hand side. Right, so this is this cubic polynomial. Right, so that's an example of a very nice continuous function. On the other hand, this function over here, x over x minus 1, this is a discontinuous function. right? So the idea here is that, of course, when x equals 1, then you have this cut here. It's going to be discontinuous here in the middle. Right? So again, we can write down functions that are continuous everywhere. We can write down functions that are discontinuous at certain points. So where I want to end today is kind of this question on the other extreme. So this is kind of a very cute, kind of weird example. And this is an example of a function that's discontinuous everywhere. So that means no matter what p you give me, I have a function that's well-defined, but it's discontinuous. Right? So this function was actually introduced by a French mathematician named Lejeune Dirichlet back in 1829. And so it goes as follows. Let's write down a function f, where I'm going to define it to take on the value 1 whenever x is a rational number, but it'll take on the value 0 whenever x is an irrational number. Right, so for example, if you give me x is equal to like the number 5, it'll plug in f of x is 1. If you give me the number like the square root of 5, then it'll give me back that f of x is 0. Right, so it just jumps back and forth between rational, irrational, rational, irrational. So my claim is that this is a discontinuous function. So the way that we're going to prove this, we're actually going to combine some of the results that you've seen so far in the class from some of the homework problems. So here's what we're going to do. Choose any positive epsilon, but I'm going to choose only the ones that are kind of small. Let's say maybe epsilon positive, but less than 1. And pick any real number p that you want. What I'm going to do is prove that there does not exist a delta such that f of x minus f of p is less than epsilon whenever x minus p is less than delta. Right? So that's what it means to be discontinuous everywhere. If you give me a p and give me an epsilon, then it says I can never find a delta since that f of x minus f of p is less than epsilon whenever x minus p is less than delta. Okay. All right, so does everyone kind of understand where we're going to go with this? How we're going to prove that this is discontinuous? Okay. All right, so here's how the proof goes. It's actually not bad at all. We're just going to do this by contradiction. So let's just assume that such a delta exists, and we'll just run into a problem. All right. Now, I'm going to use a couple of problems that you turned in for the homework last week. So in homework assignment number 10, you proved that the rationals and the irrationals are dense in the real numbers. All right, so problem number 1 in homework set 10 had you to show that the rationals are dense in R, and problem number 4 had you to show that the rationals are dense in R. So we're actually going to use these. So first, if P is rational, then I can find an irrational number x so that x minus P is less than delta. Right, because this says that it doesn't matter where you are for P, I can get really, really close by x and just force x to be an irrational number. Right, notice that I don't care at all what delta is here. Right, point is that it's dense, so no matter what you pick for delta, where you have me P as a rational number, I can find an x that's irrational. Similarly, if x is an irrational number, then I can find a rational number x that is also really, really close to P. Okay, so in either case, doesn't matter whether P is rational or irrational, I can find an either irrational or rational number x that's close to it. Okay. So now, let's just do some math. Let's take a look at f of x minus f of p. Well, on the one hand, remember that at the very beginning, we were assuming we can find a delta so that we can actually get here very close to epsilon. So on the one hand, f of x minus f of p has to be less than epsilon. But on the other hand, remember that if p is rational, x is irrational. And if p is irrational, then x is rational. So that means one of these is 1 while the other one is 0. So that's exactly this over here. Right, so again, one of them has to be 1 while the other one has to be 0. But now you see the problem, because this says epsilon greater than 1. But I just said at the very beginning, I'm choosing my epsilon so that it's positive but less than 1. So that's the contradiction. Right? Okay, so again, now we have this really weird concept about continuity. So we can either have the idea of being continuous at a point, continuous on an interval. Polynomials are continuous absolutely everywhere. But here now you have the other extreme, which is a function that's discontinuous everywhere. So no matter what I do at every single point P, I can never find a delta where I can get close and close. So this is a really, really weird looking function. Right? Okay, so that's it for me. Do you have any questions before we call it a day then? All right, well, thanks for your time and attention. So Monday then, I want to totally shift gears. We're still going to talk about continuous functions a little bit, but I do want to introduce this idea of cardinality. So I want to talk about what does it mean for the real numbers to be an uncountable set, right? And again, that won't be on the midterm. That's just going to be kind of our last official lecture. So y'all try to have a good weekend then. Remember, if you do have any comments you want to give me about votes for today's faculty meeting, I'm more than happy to hear them. You can come over for office hours. You just send it to me by email. All right. Okay, well, you all take care. See you next week then.
Thank you.
Thank you.
Okay, bye.
Thank you.
All right, you're welcome.
Thank you.